And I would like to complete the last lecture about Steiner generalized problem. Can you read what I'm writing?
Yes. Well, at least I can see.
Thank you. And just to give you some examples which were missing, and some work I did in this problem. I will not enter the details of the proof. Then after this, I would like to start speaking about minimal clusters, minimal planar clusters, and so today and tomorrow that one will be the main topic. So just to finish the Steiner generalized problem, I recall you what we did last time. Given a metric space X, which is complete, and with the Heine-Borel property, which means closed balls are compact. So you have this metric space, you are given a compact set A in X, which is you imagine it as a set of points in your space. The problem was find a set S, compact and connected, containing A, and such that the length of this set is minimal. So in this case, for 4 points, the resulting set, we have seen the construction for a finite number of points in the first lesson, and we know that in this case, the minimal set, which is connected and contains the 4 vertices of a square, is something like that. Now I would like to state, at least to state a generalization of this. So what is the result? The result we have seen last week, so a theorem, was that such S exists. There exists a minimal set. And today, I would like to just to tell you a result we had in collaboration with Stepanov in 2013, and where we generalize somewhat this result, given as before, given X as before, and A as before. So A is a compact subset of X. Minimize H1 of S, but we enlarge the class of minimizers. Instead of requiring that S is compact and contains the given set, it is much more natural to suppose these weaker conditions where S union A is connected, and that's it. We don't require S to be closed nor compact, and we don't require S to contain A, and we don't require S to be connected, but, which is very natural, we require that S is connecting A, in the sense that the union of the two is connected. Just to understand why this is more general, in these settings, for example, you can consider A a set which has infinite length. For example, if A is something like that, I don't know, is a union of some sets which are not curves, something like that, then the problem makes sense, and you will find something like this as a solution. So you want to make the union of the two sets A and S connected, but you minimize the length of S, not the length of the union, which in this case would be always infinite, because if A has infinite length, the problem makes no sense at all. So this is nice. We also don't require S to be closed, because what happens is that, in fact, it is one can prove that it is locally closed, and this is due to the fact that if you take a set with finite length and which is connected, this is a very strong condition. You can get a lot of information from these two facts, and so closedness is not really required here. Okay, maybe another example. You can have the set S can also be disconnected if you have something like this, maybe. If you have a set A like this, you expect the minimizer to be something like this, two disconnected curves. Okay, I also would like to show you that this problem, or the original one, which we have seen last week, the original one, the first statement, the first theorem is due to Ambrosio and Tilly. Just a few examples to show why living in a metric space is so useful. You don't require to have very strange metric spaces. For example, if X is a subset of R2, you can take a subset of R2. This is also interesting. You can take any closed subset of R2 so that X is complete. And this enables us to formulate a problem with obstacles. So you can remove from R2 some holes, some open holes. So you remove from R2 something like that. And you take, X is the plane without the yellow regions. And maybe you take a set, simple set like 3 points, something like that. And what you expect to find here is a solution like that. Maybe. Maybe here we have a triple point and something like that. So clearly in a metric space, you don't have the concept of straight line, but we have also a regularity result. So in the theorem I mentioned here above, We also have some kind of regularity, which you can state like that. You have some properties of the minimizer. The first one, we expect S, the resulting network, to have no loops, so that it is a tree or maybe a forest, as we have seen before, because S can also be disconnected, but it has no loops. Not only that, also the closure of S has no loops, which is a little bit stronger. Okay, because you see that the closure can have a point of, if you take the closure, you are considering also the points which are in the set A. And if you take S outside the given set A, this is a topological tree, or okay, is maybe a forest, I should say, is the union of countable many Lipschitz curves. Okay, it is rectifiable, so this is not strange. And each tree, since it has no loops, this is a union of trees, and each tree has countable many vertices and edges. So it is a countable tree. This is not surprising because otherwise the length would be infinite. If you have, if you have a lot of edges, at least the length would be infinite. The fact that also the vertices are countable many is a consequence of the third fact, which is that S away from the given set A is locally. So if you consider S and remove a neighborhood of A, this means locally, is locally a finite minimal tree. And so this means that you have locally a finite number of vertices and a finite number of arcs, and the arcs, then you may apply the information you have for the finite problem. The arcs are geodesics, and so on. If you have some property, so if you are in R2, for example, you can say that the vertices have order 3, and that the angles are 120 degrees. So you can recover the usual properties of classical Steiner trees. So some examples, I would like to show you some examples where we expect to have infinitely many Steiner points. One example is, I can imagine, this is not really proven, but I think it should not be so difficult. If you take a countable compact set, so A is a countable set of points, and you place them. Okay, it is better first to draw the expected minimizer. If I would like to have a minimizer which is like that. And you can imagine that one should be able to obtain a set which has infinitely many triple points, and this should be a minimizer if we choose this set of points, which is compact and countable. And you see that as soon as you remove a neighborhood of the accumulation point, this tree is actually finite. So we get the result, so the tree is actually locally finite. Another example, which is maybe more interesting, and this is a paper in collaboration with Stepanov and Tepliskaya. We are able to prove that there exists a minimal set, which is something like this. You take a branching tree with infinitely many branchings, like that. We are in the plane in these examples. And so the given set is the limit of these branches. And as you can imagine, so the construction is you take, you want to consider a segment here of length L1, and then we consider two segments of length L2. So at each level of the tree, the segments have all the same length. And we are able to prove that if this length lambda k go to 0 sufficiently fast, then this is actually a minimal tree. So we have lambda 2, lambda 3, lambda 3, lambda 3, and so on. And you can notice that the given set A is more than countable, is a counter-like set. So let's say the cardinality is the same of the counter set, while anyway the number of Steiner points, since we know that it is locally finite, it is anyway countable. So anyway, the number of Steiner points, so the branching points, is countable. So this is very difficult. It was very difficult to prove. Seems very natural. And if you like, here we have, I think it is an open problem. The first example we tried was with a self-similar tree. So self-similar means that the length lambda k is lambda 1 to the power k. So at every step you reduce of the same amount. So the every branch is similar to the whole set. And this we are not able to prove that in this case. Is it minimal? We don't know. We require the length to go to 0 more quickly than this. Okay, you can find many other examples by taking subsets of a segment, 0, 1. If you take any subset, any compact subset of 0, 1, and you take also the point 0 and 1, it is clear that the minimal set is the interval itself. So 0, 1 without A is, of course, is minimal, because it is minimal even if you only have the two external points. And this gives you a lot of bad examples where you can check that our result is actually true. For example, you can take the complementary set of a Cantor set or something like that. And you can see that S can have infinitely many connected components, and so on. So this was 3, 4, 5, just to give you something to think about, if you like. What about if A is not bounded? Because you see now we have very little requirements on the set S, but we have the same requirements on the given set A, which is a compact subset of the metric space X. So it is nice to have examples where where the theorem fails if A is not compact. And if A is not bounded, you can find such an example. You can take, for example, A, which is a line, and something which is asymptotic to it. If you have something like that, this is not bounded. And of course, you can connect this set with arbitrarily small length, but there is no minimum because the empty set does not connect. A is not connected, so you need at least some length, but arbitrarily small. So here there is no minimum. And the last example I want to show you is what if A is not is bounded, let's say, but not closed. And here we don't have actually a counter example, so this is open. We don't know. It means that I have no example of a bounded but not closed set A such that to connect it, you don't, the minimal set connecting it does not exist. But I have a nice example to show you just to understand that something bad can happen. So, for example, take this set A, you take a set like that, a point, then you take some segments, and you take infinitely many of them, converging to the midpoint here. So this set A is the sequence of these segments, but you don't take the limit points, so that the minimal set with our formulation exists, and it is this one. You take this set S, and as you can see, S union A is connected. So this actually, it is easy to understand that this is the minimal possible length, you need to connect this set A, but it is not pathwise connected. So maybe it is true that if you take any bounded set A, there is a minimal set connecting it. But it is true if you require, if you take topological connectedness and not pathwise connectedness. As you can see, this set A has length, has infinite length. Otherwise, it would be also pathwise connected. Okay, so I would say that this is what I would like to say. I don't enter the proof of this theorem. Maybe just to understand, of course, we use the machinery developed by Ambrosio and Tilly, and something that it is some idea you just to understand why this result is true. So why we only require S. We don't require S to be closed nor connected. And the one point is that if you have a set with finite length, then also its closure has finite length and has the same length. So this is true if S is connected, actually. If you have a connected set with finite length, even if it is not closed, you can take the closure and you don't enlarge the length of the set. Okay, but we don't know that S is connected. So another idea is to split S. Consider so work on the connected components of S, and you can prove that these connected components only can accumulate. Actually, you can have points which are limits of different connected components, but such points are always in the given set A. So away from this given set, the connected component are far away from each other, so you can work with them. Okay, and then you have a generalized, or maybe localized, Golab theorem, which is nice. This was proven. This was known in the Euclidean space Rn. And we extend the proofs following the idea of Ambrosio and Tilly in any metric space. It is. We have seen last week. We have seen the idea of the proof of the Golab theorem. The same idea applies to prove that something like that. If Sk converges uniformly to S. Okay, and Sk are connected, and we can suppose also compact connected. Then you can localize the Golab theorem, the H1 length of S minus or less S. Okay, in an open set, omega is less than or equal to the limit of the length on any. So Golab theorem holds true on any open set. So the idea is to remove the set A from the metric space and And so if you have a minimizing sequence, you consider Sk union A, which is supposed to be connected, and you apply the localized Golab theorem on the complementary of the given set A. Okay, so this was just to tell you some examples. I think that even if you haven't attended the last lesson, this is self-contained. Some idea, not really proofs, but just to have some ideas, and maybe if you are interested, you have some open problems you might think about. Okay, so now I would like to start a new topic. So I don't know if there are. It is a good time if you have any questions about the Steiner problem. Otherwise, I would like to talk about minimal clusters, and let's say planar clusters, which is a problem similar to the one of Steiner. Okay, so so what is a minimal cluster? The problem, roughly speaking, is the one. So let's say we are in the plane. In this case, we don't. Something I will say is true in any dimension, but in the plane we have much more results that I can show you, and it is much more simple to explain. So in R2 we are given some areas A1, A2, AN, and different positive numbers which represent some given areas, and you want to find maybe I can say like that, a fence in the plane which encloses of minimal length as before. Find the fence of minimal length separating and enclosing n regions with the given areas. So, for example, if I take two areas, A1, maybe we can take A1 equal to A2 just to start with, maybe equal to 1. What is the minimal fence? The minimal, let's say, could be a network again, which encloses two regions of area 1 and with minimal length. If you think of a single region with area 1, if you have a single region of area 1, then we know the isoperimetric problem that the minimal enclosing is a circle. So you may think about taking two circles, but this is not optimal, because if you move a circle against the other one, and you can imagine that these are soap bubbles, because if we state the problem in R3, you can imagine that a soap bubble, a bubble cluster, so a cluster of many bubbles, is solving exactly this problem. just replace area with volume and replace length with area. And so if you have some bubbles, you blow some bubbles, you have some fixed amount of air within the bubble. And when you move it, you can imagine that the amount of air is fixed. This is not exactly true, but just imagine like that. And when you put you bump two bubbles together, what you find is something like this. This is what is called a double bubble. Here you have area 1, and you have two arcs of circles with equal radius separated by a straight line. And this is actually the optimal way to enclose and separate two regions of given equal area in the plane. Okay, what we are going to minimize is the total length of this cluster. And the main aim of the lesson of today would be to prove that actually the problem with only two regions, which is the simplest one, if you already know the isoperimetric problem, the isoperimetric problem is the case n equal 1. So you have a single region, and we know that the solution is a circle. Well, if you have two regions, this is not so easy as one can imagine. And I would like to show you the proof that how we can find the minimal double bubble enclosing two given areas. If the areas are different each other, one is smaller than the other, what we will find is again an arc of circle, and then a larger one here, and then the interface in between is another arc of circle. So maybe this is A1, A2, and A1 is less than A2. Okay, I would like to formulate this problem in a somewhat formal way, and this is not so elementary. To formulate this problem, you should either use the perimeters, so formulation. You have two possibilities with sets of finite perimeter. This is what the Italians prefer. And otherwise, you can use rectifiable currents. And even in this simpler case, you need some of these tools. I would like to present the problem with perimeters. I have no time to give you all the formal definition of what is the perimeter of the set. So just some idea. You can find easily. You can find books where this is explained in detail. I would like to give you something. Something about the cluster, which is a little bit more difficult to find. This one, if you like it, if you need it, you can. Maybe you know already, or you can study by yourself. So if A is a measurable subset, let's stick with R2, but of course this can be done in any dimension. You have a set A, and you can define the perimeter. We write like that: perimeter of A is, and here I would give you an intuitive definition, is the length of the boundary. And actually, if you know that a set, so you can define the perimeter in very many different ways, much different one from the other. Different ways, you always find the same concept. One possibility is just to approximate. Maybe you have a set which is a very bad measurable set, but you can approximate it with regular sets. So sets which have a regular boundary, and you take so you take the limits of the perimeters of the approximating sets on every possible approximation of E. So this is a possible definition. You can even take polyhedral sets. You can approximate E by polyhedral polygons, let's say, something like that. Or you can develop the theory of BV functions and take the total variation of the characteristic function of E, or you can define it with the Stokes theorem in a weak way, and you always get the same result. So the idea is that if a set E has a finite perimeter, maybe it is maybe the boundary has some angles, but actually there is a notion of reduced boundary which gives you a rectifiable set. So up to a set of 0 measure, you can identify the boundary of your set, and in almost every point of the boundary you have maybe here I have something rounded, I don't know. These sets can be very bad, but at least you have a notion of normal vector to the boundary of the set. You have a nice notion of boundary satisfying Stokes theorem, and you have a notion of almost everywhere you have a normal direction, so you have a tangent plane, and this boundary is rectifiable. So how can we use perimeters to formalize the problem? So we say that an N cluster, so this will be a cluster composed by N regions, is let's say a vector of sets with finite perimeter. So is a nuple, which I will denote like a vector, E with a vector notation. So this is E1, E2, En. Okay, I'm thinking about something like this: E1, E2, En, E3. So you have many of them, En. And what we would like to require, we require that these sets are disjoint. So the intersection has measure 0 if E is different from J, and that's all. That's all. Since the sets are disjoint, it makes sense to consider the complementary set, the outside, which we can define as E0. So the cluster is this one, A1. You have different regions, A2, A3, A4. And we can define the outside E0 is nothing else but R2 minus the union of EJ. In this way, it is natural to define the perimeter. How can we define the length of this cluster here? You see that if you consider a single region, E1, E2, En, the components of the cluster, we call them regions of the cluster. So we have N regions. If you consider the perimeter of a region, you get the length of this fence here, this curve. And so what happens if you sum up, if you take the sum of the perimeter of each region, what happens is that the internal curves are counted twice. Okay, you see that here this curve is counted twice because you sum the perimeter of A1 and the perimeter of A2. And okay, so if in this sum you take also the external region, so you start from 0 to n, you have n plus 1 terms, then every curve is counted twice. So you can divide by 2, and this is a sensible definition of the perimeter of our cluster. Okay, because you see that the perimeter of the outside, which is equal to the perimeter of the union, is this one. And so if you consider also the outside region, every arc is counted twice. Okay, so the problem can be easily formulated now. Also, I give you another notation, which is the measure of the cluster. And this is a vector. This is the vector of the measures of each region. The measure of A1, which is the area of A1, the area of A2, and so on. So this is a vector in Rn. The perimeter, of course, is a scalar number. And so it happens that the minimal clusters solve a minimization problem with constraint. So we say that a cluster is minimal with given areas, a vector A1, AN, positive measures. Okay, we will consider the comparison between vectors. It is useful here to consider it as point-wise, so component-wise comparison. So I say that the vector A is larger than 0, larger than the vector 0, if every component is positive. So we say that a cluster E is minimal with given areas if the perimeter of E is the infimum of the perimeter of any cluster, such that the measure is given. The vector of measures of the cluster is the given one. And of course, also E has the same condition. Okay, so we have a constraint. The areas are fixed, and we minimize a functional, which is the perimeter. Okay, now one can think about existence of minimizers. So if you are given a vector of measures, if you're given the an n of measures, you ask if there is actually a minimal cluster which has exactly such measures. And this is true. This is true in a very general setting, not only in the plane, but it's not as easy as one can think about. I will not enter the details of the existence problem, just to understand what is the difficulty. So we have a compactness theorem for sets with finite perimeter. So we have a compactness which is stated like that if you have a sequence of sets of single sets EK with a bounded perimeter. This is less than some fixed constant L, finite. And so they have uniform, you have a uniform bound on the perimeter, and they are also uniformly bounded. So EK are all contained in a large ball, BR. Then there is a compactness. So you have a subsequence. There exists a subsequence AKJ such that AKJ converges to a set E, and the convergence you can think it in a as an L1 convergence, which means that the measure of the symmetric difference is going to 0, and also you have semi-continuity. So when you have a converging sequence, you know that the limiting set has perimeter which is not larger than the limit of the perimeters. Okay, J. And these are general results. So if you are if you live in a compact subset of R2 and you have a single region, or actually, if your problem is stated in a compact subset of Rn, the existence of minimizers is really trivial, because you take a minimizing sequence, you take the limit, and the limit is your minimal cluster. And this you can do for a single region, but it's the same if you take a cluster. If you take a sequence of clusters, each region, you can make each region converge to some region, and what you find is that the limiting regions are disjoint, because in the sequence they are disjoints, and these properties passes to the limit, and so you get that also the perimeter of the cluster is semi-continuous, and you get the existence of minimizers. The difficult point here is when you are not in a bounded, in a compact set, in a bounded set. We are in R2, which is unbounded. So what about, the problem is all about boundedness, boundedness. And these problems, you can find it also in the isoperimetric problem. If you, of course, if you try to minimize the perimeter of a single region, if you have a single region and you take a minimizing sequence, well, maybe this sequence is going to infinity. You take a sequence of sets which is going to infinity. Maybe it becomes very close to a ball, but it is going to infinity. Also, it may happen that it splits. You can have a set which is composed by two disconnected regions, and the two disconnected regions, one maybe becomes smaller and smaller, but maybe they go to infinity in different direction. And so if you have only one region, you can avoid all of this problem, just noticing that if you take the convex envelope of your minimizing sequence, of each term of your minimizing sequence, you decrease. So actually, first of all, if the set is not connected like this, you can move the connected components so that you get a connected set which has the same areas and same perimeters. So you modify your minimizing sequence, and you obtain connectedness of the sets. And then if the sets are connected, you can convexify them, and so you decrease the perimeter and you increase the volume, so you can rescale to get the same volume, and you decrease again the perimeter, and so you find a better minimizing sequence composed by convex sets, and then you can move them so that their center is fixed, and so these sets are bounded, have a bound on the perimeter, so they are all contained in a large ball. This is okay, a very informal proof of the isoperimetric problem, so that there is a set which minimizes perimeter among all sets of given area. If you have a cluster, the problem is a little bit more tricky, because if you have a cluster, you cannot convexify. We see that minimal clusters, we expect minimal clusters not to be convex. You see in these examples here, the double bubble, the whole cluster is not convex, and also some regions might be not convex. This region is not convex, for example. So you don't expect minimizers to be convex. You cannot use convexity. So the point is that you need a more precise compactness argument, which holds true also in the whole space without a requirement on equiboundedness of your sequence, and so you have what is called the concentration compactness. Okay, this is something like if you have a minimizing sequence of clusters, maybe you have something like that, and you might have okay, now actually in the plane there is a shortcut. In the plane, okay, in the plane you don't really need this result. In the plane you have another nice result, which we have already seen last week. So once you suppose that your cluster is connected, so all the boundaries touch each other, this you can assume by modifying the sequence. And then you know that the diameter of your cluster, whatever it means, it is the diameter of all the union of all the regions can be estimated by the perimeter of the cluster, because because we are in because our boundaries are one-dimensional in this case. So in the plane there is a shortcut, and you can easily get boundedness, because once the diameter are equibounded, because the perimeters are equibounded, you can move them so that they all stay in a given large ball. Otherwise, in the space or in n dimension, you need some kind of compactness. So here, what happens? It may happen that some regions have long tentacles, long thin tentacles, and maybe you have, even if they are connected, you can have. So this is a surface, and this is a tube, something like that. And of course, you can construct a tube which has a very small volume and also very small surface area, while in the plane the length of the tube cannot be small. And so it is possible that your cluster is broken into pieces which go to infinity in different directions. And what you do is you track these different sequences, and you find many limiting clusters, and you prove that the area of the limit is preserved, and so each limiting cluster turns out to be a minimal cluster, but then you can put them together and show that their union cannot be minimal, because because you bump two different sets one against the other, so you expect minimal sets to be connected. So if the sequence breaks up and goes to infinity in different directions, you get different limiting clusters, but then you take them you put them together, and you know that what you get cannot be disconnected, and so you have a contradiction. So, however, this we don't really need if we are in the plane. So I can move over this. Okay, so let's assume that we have existence of the cluster. What we want now to get is some result of regularity of minimal clusters. Planar. I will always speak about planar clusters. So maybe the main tool in the regularity of minimal clusters, actually this is also used in the existence. It is a little bit hidden in the previous explanation, but if you are in high dimension, in the space, or in higher dimension, you also need for existence, you need this lemma, which is Algren's lemma. Okay, the idea is that to prove regularity properties of a minimal set, you want to make small variations of your cluster. And so this lemma enables us to do so, to consider variations of clusters. And so if you have a set, just consider a single, think about a single region. So a set E with finite measure and finite perimeter. And this is true in Rn, not only in the plane. Okay, so for every small radius rho, there exists. So let's draw a picture. You have here a set E, and the idea is that somewhere, this is a set of finite perimeter, so you can find somewhere a point where the boundary has a tangent plane. You take a small neighborhood of this ball, which is smaller than the given rho, or maybe equal to rho. And the idea is that I am able to make a modification of this set in this small ball. We can modify the set so that we can change a little bit the measure of the set. So we want to construct a variation E prime, which has a measure which is slightly different from the measure of E, and such that the perimeter maybe increases, but not so much. Okay, so how can we write this? And there exists C larger than 0. This is a constant which depends on the set, and more or less depends on what happens in the set. In the small ball, you can take every ball in the boundary of the set, and the constant C is something like the average curvature of the set in that point. So if the set has a large curvature, C will be large. If it has a small curvature, it is small. But anyway, there exists some constant C, and there exists an epsilon, which is a small area. So the epsilon is the largest possible variation in the area we can do. And there exists a point X, which will be on the boundary. So we don't really need to state, but this will be in the boundary of E, actually the reduced boundary where we have a tangent plane, such that for all given measure M, such that so we want to modify the measure of the set E by a small amount M, which can also be negative. We can decrease also. So M is a real number with small absolute value, smaller than the fixed epsilon. But for every small variation in the measure, in the area of the set, there exists a set E prime, which is this small variation, so such that the symmetric difference, so the variation is all inside the small ball B rho X, and such that the measure of E prime is exactly equal to the measure of E plus M, which can also be negative. And the perimeter of E prime, and this is the point, is not so much large. It is not larger than the perimeter of E plus this constant C. Okay, a posteriori, we know that C, which is the the curvature of the set here, C is defined. Okay, you cannot actually define the curvature, the pointwise curvature, but you can define an average of it. So this C is somewhat an average of the curvature, and we know that the variation. So the idea is that the curvature is somewhat like the derivative of the perimeter with respect to the measure of the set. So here we have this constant C times the measure M. Okay, so here we have a length. This is a length. This is an area, and C like a curvature is the reciprocal of length, is something like 1 over a radius, and so this inequality makes sense. Okay, and I don't want to enter the details of this lemma. Just the idea is simply to okay. Let's zoom in the ball. Here you have your set, a nice point here. And the idea is that here you have a normal direction and you are able to define a normal vector field, so a unit vector field in the direction of the normal to the set. And then you take this normal field and you make a cutoff so that it has a compact support inside the ball, and then you define a family of diffeomorphisms which are obtained starting from the identity and following this vector field. Okay, so you are able to construct diffeomorphisms which follow the direction of this field and which becomes the identity outside the ball. And so you are able to evaluate, to estimate how much the measure of the set changes. So okay, you for every t small enough, you define a diffeomorphism phi t. And you define E t as phi t of E. You modify the set with this homeomorphism, and now you trust me that you can track how the measure of this set is changing, and this is continuous in t, and the derivative of the measure is positive since you are going in the normal direction, and so you can increase or decrease the measure for a small amount, and then you can estimate the perimeter of the set E, and you find using Stokes' theorem, you find the desired estimate. So this is maybe the main tool, just to understand how you use this. Okay, the first regularity property is a very simple one. A minimal cluster has finitely many connected components. This might seem strange because I said that the cluster is composed by n regions. So why it is not n, the number of components? Well, because the components of a cluster are not the regions. You might okay, you might expect that you don't know if the regions are themselves connected. So even if you have, let's say, a tree cluster, so a cluster with 3 regions, you have one region, another region, and another one. You have 3 regions. Well, you cannot assume that these regions are actually connected. It may happen that your minimal cluster has some more connected components, maybe infinitely many a priori. Okay, maybe here you have the orange one, and also here, and then you have maybe this one here and here, like that. So it is not, a priori, it is not clear that your minimal cluster has finitely many components. But, okay, so this is maybe A1, and also this is A1, A2, 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 A3, and so on. Okay, but so the point is that, okay, maybe you have infinitely many components, but then since the measure, the total measure of the cluster is given, is finite, and the total perimeter of the cluster is finite, then if you have infinitely many components, there are such components which are smaller as you like. So you have very, very small components, and the idea is that you can remove a component if it is very small. Okay, the idea is take, so you have, here you have many regions. Each region has its own constants given by the Algorithm's lemma. So they have their constant C, epsilon, and a point X on each region. So in each region you can find these little balls somewhere where you can make some variation. And also you can find regions between two different regions if you need to. And the idea that you have many constants, you take the smallest one, and so if so you have you have an epsilon by Algren lemma, and you have by contradiction you can suppose there is a component C component of some region which has a measure which is smaller than epsilon. Okay, so you want to make a variation of your cluster, and the idea is that you remove this component. So you take a cluster A prime obtained by E by removing. This is a little bit formal writing, because I should say how each region is constructed. So A obtained, E prime obtained by E, removing C. And so if you remove C, you modify, you are forced to modify the measure of the region which was containing C. So you use Algren's lemma to recover the original measure, so that you get the same measures, and recover the measure with Algren's lemma. And so what you get, that the measure of E prime is equal to the measure of E, because you have recovered the missing area, and you can estimate the perimeter of E prime as the perimeter of the original cluster. Now, since you are removing a component, a very small component, here you are removing a very small component C. What happens is that you remove some perimeter also. You decrease the perimeter by removing a component. How much perimeter can you remove? The idea is that if the component is external, you simply remove C, and you remove the external perimeter you have here. But even if this is small, you know that there is a region which touches C, and since there are you have n regions, you have a fixed number of regions, you can gain if you give the set C, instead of removing, this is not correct. You don't remove C, you give C to a neighboring to another region. You give C to an adjacent region, and you choose the one which has the most perimeter in common. And since there are n regions, at least one of them has a perimeter which is the perimeter of the connected component divided by n, because you have only n different regions. You consider also the external region, so you consider all regions different from the one C was belonging to, so you have n different regions, counting also the external regions, and at least one of them has a boundary in common which is larger than the perimeter of the components minus n. And then this is what you gain. What you lose is given by Algren's lemma. It is a constant C depending on the region you have chosen, but there are n of them, and then the measure of the variation. And so we have a competitor, E prime, and if E was a minimal set, this perimeter should be larger than the perimeter of E. And so you get, okay, what you get here, here you have perimeter of E. Okay, you get that the perimeter, you make the difference, perimeter of C over N is less than or equal to C times the measure of the component C. Okay, but now we can use the isoperimetric inequality, and if you have any set C with some measure, the perimeter is larger than the perimeter of a circle with equal area. So if the measure of C is equal to the measure of BR, let's say, a ball with radius R, then the perimeter of C is larger than the perimeter, how much? The perimeter of B, which is equal to 2 pi R, which is so let's say, okay, let's say here we have a constant. Okay, we want, I was trying to compute the constant, but maybe I get lost. So which is the constant? The measure of set C can be estimated by a constant which is should be 4 pi. Yes, I think so. The perimeter of C squared. Okay, if you rescale a ball so to have the same measure of C, you get this isoperimetric inequality. And so you are done, because you see that now you obtained that the perimeter of C, you divide by the perimeter of C, and the perimeter of C is larger than 1 over n C 4 pi. And so you cannot have connected components with arbitrarily small perimeter. Okay, and maybe I could stop here. I could stop here because I need some time for the next statement. So tomorrow I will continue with the regularity properties of these minimal clusters. And as I said, my aim is to find at least what are the minimizers with two given regions. So the double bubble problem, which is very elementary, but I would say a very nice and smart argument I would like to show you. And if there is some time, I think yes, I can talk about what happens with three regions, so the triple bubble, and maybe a little bit about four regions, which is something that I have worked on. So, so thank you for your attention, and see you tomorrow.
Okay, thank you so much.